in section 8.1 in Calculus 2, and my computer is taking a vacation from me, and so I'm going to use this thing called a pen and some paper to write the problems that we're going to do today. And I'll scan these notes and you'll have them, so you can just write along with me, or just print these out on your own if you're just listening. So this lesson, this whole chapter is really about puzzles, just solving integration problems, and you get better at these through practice. So if you ever wanted to just use your textbook, which you can access online on the button that says entire textbook, and then you can go to, let me show you how to do it. Like, you go to the entire textbook, which is this button right here. I don't know if you can see it. This button right here is entire textbook. And then you can scroll down and click on the chapter. And then you can go to like section 8.1. You can read the section in here, and he goes through like 10 different examples. And so there's 10 resources for you of the different types. I'll do different examples today. And then the textbook exercise set is actually like, back in the day when you used to do homework out of the book. That's all this is. That's just the book, the questions in the book. And so what I'm going to do is I'm going to put up the instructor solution manual to this chapter. I'll make that available to you. So if you wanted to just go in and practice more problems besides the online homework, just any of these problems, like all of these evens or something, you could then check your answers in the instructor solution manual. Or you could just look at how the solutions are worked. Okay, so this chapter is really about practice. So the more time you have to practice these, the better. Like if you did 5 a day, it would be really fun and neat, and you'll get smarter, because this is definitely brain building stuff. Okay, so that is that. So we'll go ahead and let's just start working. I hit the laptop button, but I have to use the document camera. Okay, and so let's just start working some problems for techniques of integration. Now, one thing that I will be referring to, and I encourage you to use, is the integration formula worksheet those formulas that we have, the basic integration formulas. You guys remember these you may have it already printed out, and it's available, and I think it's under additional resource on your computer. You should have that, because you're going to want to look. What we're going to do is we're going to try and work on getting our formulas, or the problems that we're looking at, we try to finagle them to make them look at like some of the basic integration formulas, so that we can use them to help us. Okay, so back to the document camera, and we will work some problems. So this is just integration fun. And we're just going to work until we hurt, Burn. Okay, so let's just do the first one. This is like a warm-up. The warm-up's always easy. Okay, so this is just a basic substitution problem, right? What would the U subs, can you see that okay? All right, hopefully. Good. Okay, what would the U substitution be on this problem?
X squared.
All right, so we'll let U equal 8x squared plus 1. So then du will equal 16x dx, which is exactly what we have there, right? So this is going to be the antiderivative of du over the square root of u, which is the antiderivative of u to the negative 1/2 du, right? So we just add 1 to the exponent and put it over it. So this is going to be u to the 1/2 over 1/2 plus c, or 2u to the 1/2 plus c, which is 2 square root 8x squared plus 1 plus c. Right? Okay, and remember, every integration problem can be checked by differentiating your answer. So if I were to differentiate this, I should get back to the integrand. So if I wanted to take the derivative of this, I'd write it like that first, right? And then the derivative, if that were y, obviously the plus c, that's just going to be 0. I'm going to put the plus c over. So y prime, I'll have the 2 will tag along, the 1/2 will come in front. I'll do 8x squared plus 1 to the 1/2 minus 1, which is negative 1/2, times the derivative of the inside, which is 16x. So those 2's cancel, and I do get exactly what my integrand was, 16x over the square root of 8x squared plus 1. So all of these problems are self-checking, right? So that's kind of fun. All right, so let's try another problem like this one. How about the antiderivative of dx over the square root of x onto the square root of x plus 1? What would be a good u for that one? Let's let u equal the square root of x plus 1. Then du will be equal to 1/2 x to the negative 1/2 dx, right? Well, that's 1 over 2 square roots of x dx, which is almost what we have here. We have dx over the square root of x. To get rid of that 1/2, we can just say 2 du is equal to dx over the square root of x, right? So we'll put the 2 in front. We'll have the antiderivative. We'll have the du over, that went along with the dx because it's du was dx over square root of x, so that's replaced with du, and then this is just u. And what's the antiderivative of du over u? Yes, that's 2 ln, and you have to do absolute value, plus c, but the square root is always, that's positive, plus 1 is just going to be positive, so now you don't need it. So it's 2 ln square root x plus 1 plus c. You don't need it because you know that it's positive. Okay, all right, so then let's try another one. How about this one? The secant, the antiderivative of the secant of t over 3 dt. How will we do that one?
What does that say? It's cut off.
Which way is it cut? This
Down.
down?
Dirt. Yeah, right there. You're good.
Okay. This is always fun. All right. Do we know the antiderivative of the secant? Well, if you go to your sheet, let me see if I'm ready to. Yes, it is on our sheet. Number 10, the antiderivative of secant is ln secant u plus tangent u plus c. Okay? So that means that we can go back here to our notes. And this should be easy enough. If we just let u equal t over 3, then du is equal to 1/3 dt. which is almost what we have. We just need a 3 in front. So this will be 3 du equals dt. So we'll put the 3 in front, the antiderivative of the secant of u dt. And according to the formula sheet, the antiderivative of secant u is ln, so we'll have 3 ln, the absolute value of secant u plus tangent u plus c, which will be 3 ln absolute value secant t over 3 plus tangent t over 3 plus c. Which is really interesting to think that if you take the derivative of this, you're going to get back to just secant t over 3. Probably have to do a little work, but I just promise it is. All right. How about this one? The antiderivative of 9 du over 1 plus 9u squared. All right. Now, there's a few that just come up enough that they should be they should just sort of live in your brain. All right? And one of them, this is one that should live in your brain. First of all, you should recognize that you can pull this 9 out front, and you're going to have du over, humor me here, 1 plus 3u squared. Do you agree with that? Okay. Now, when you look at your sheet, hopefully you see that this is your friend, the inverse tangent. That when you have du over number squared plus variable squared, it's always the arc tangent. The arc tangent comes up a lot, the inverse tangent. So just want to kind of remember that one. And so we will come in here and we will use the from formula sheet. The formula sheet told us that du over a squared plus u squared, where a is just a number, is equal to 1 over a arc tangent or inverse tangent u over a plus c. And so in this case, we will have nine. The 9 is in front. So, sorry. On this is actually, it's kind of I don't know how I want to explain this. It's frustrating because when you have so many, it looks like you have exactly du over u, but see, I have too many letters. Would it be okay if I write this as 9 and then antiderivative dx over 1 plus 3x squared, just for a second, so that you can see that in actuality we don't have exactly this formula, because we don't have exactly just a u here, because our u is equal to 3x, right? So u is equal to 3x, And so then du is equal to 3 dx, right? So if we want to replace dx with du, we need to do a 1/3, right? And so back to this, 9 antiderivative dx over 1 plus 3x squared will be 9 over 3, because I'm going to put my 1/3 out, and then antiderivative du over 1 plus u squared. And so now it's exactly in the form that we need. And so we can say 3 and then 1 over a, which is just 1. So then arc tan u over a, which is just going to be u plus c. And then our u was the 3x. So this is 3 arc tan 3x plus c. So that one, it's kind of weird because it had that u already in it, and it was actually better if you don't confuse your u's. I hope I did an okay job on that. You have to handle this 3x there and take 1/3 of your of the whole thing. Does that make sense? Because like right here, this is assuming that this is just some variable squared. And so if you have a coefficient in front of that variable, you need to handle that by plugging it in front. Okay? All right. So now, let's do another one. Let's do, this one looks fun. So that was 4, so let's try number 5. I'm moving my paper, Brandon. Can you see that 5? Okay.
Yes.
Antiderivative 3 to the x plus 1 dx. Okay. On this one, there's kind of 2 options that you can use to work this. What jumped in my mind right away was to write 3 to the x plus 1 as 3 to the x times 3 to the 1. Because, you know, when you're adding in the exponent, that's like you're multiplying. That's sort of my first thought. So I would write this as the antiderivative 3 to the x times 3 to the 1 dx. And then I would just take that 3 to the 1 out front. Right? And then we learned how to anti-differentiate this. Do you guys remember how you anti-differentiate this? How do you is it on the sheet? Let's see. This one may not be on the sheet. Let's see if it's on the sheet. There's an e to the, oh, there. I see it. Oh, you're not looking at it. Sorry. Do you see which one it is? It's number 4, the a to the u. It's 1 over ln a to the u plus c. Make sense? So it's just like e to the x, the antiderivative e to the x, e to the x, except you have to put a ln, the base, on it. That's kind of how I remember it. So this is going to be 3 times 3 to the x over ln 3 plus c. So when I'm looking at the solution manual, they actually write this back as 3 to the x plus 1 over ln 3 plus c, because, you know, that is like that. So in the solution manual, they actually did a u substitution right there, which is fine also, however you want to work it. Okay, how about a definite integral? So let's look at another one. This is the antiderivative from 0 to 1/6 dx over the square root of 1 minus 9x squared. Now, when you don't have like if you had 18x or negative 18x or something x in the numerator, you would be able to do a u substitution on this one. But you don't, and so then that's when it's normally going to be one of those inverse tangent ones or inverse sine or something like that. So you want to go back and look at your sheet and see if you can fit that in to be one of them. And I'll let you look at that. Do you see one of them that it looks like? Yeah, it looks like it's going to be an arc sine, but again, remember you are going to have to do a u substitution. You're going to have a little bit of numbers in there. Okay, so if we let u equal, does it make sense that our u should be 3x because it's 9x squared, and it's always a squared minus u squared. So u equals 3x. The du is equal to 3 dx. So we're going to put in a 1/3. So we'll have 1/3. Antiderivative. If our u is 3x, and we can go from 0 to 1/2, and then this will be du over the square root of 1 minus u squared. And from our formula sheet, we see that that is the inverse tangent. So we're going to have 1/3, and it's 1 over a, which our a here is just 1. So then it's just going to be, did I say arctangent?
Yeah.
I meant arc sine. Inverse sine, and then u over a. So u, and since I changed my limits, I can just use the u now. So u over a, which is just going to be u, and then we won't have a plus c because we have definite intervals. So this is from 0 to 1/2. Okay, so then this is 1/3 times the inverse sine of 1/2 minus the inverse sine of 0. And so the inverse sine of 1/2 is, that means for what angle is the inverse sine, or is the sine ratio 1/2? So if you're having a good day, you should think pi over 6. So this is pi over 6 minus, for what angle is the inverse sine 0? That's just 0. And so you get pi over 18 as your answer on this one. So that was kind of fun, right? So you could do it with your calculator, but it wouldn't necessarily give you the pi over 18. So, okay, let's do one more and then we'll look at some techniques. If you, this one I was looking at it this morning and I thought it looked kind of fun. The antiderivative of dx over e to the x plus e to the negative x. All right, this is one of these problems where you have to be cute, okay? And one way to be cute is to multiply by 1 in a convenient form, okay? So the cute way that I'm going to multiply by 1 is e to the x over e to the x, okay? So clever trick is to multiply by 1 in useful form. Here, e to the x over e to the x is useful, and you'll see why in just a second. Okay, so I'll have the antiderivative dx over e to the x plus e to the negative x times e to the x over e to the x. Well, what that's going to make is antiderivative e to the x dx over e to the 2x, and then e to the negative x times e to the x is e to the 0, which is just going to be plus 1, right? And then if I let u equal e to the x, this is really snazzy, then du is equal to e to the x dx, right? Okay, so that is right here. And what I can do right here is I can, instead of e to the 2x, I can put a u squared. So this will be the antiderivative of du over u squared plus 1. Snazzy? It's like double snazzy. All right, and then finally, what is that one? That's your friend, the arctangent. Du over 1 plus a squared plus u squared, so where your a is 1. And so then this is just going to be the inverse tangent of u, which is e to the x plus c. So that one had 2 tricks in it, and I don't know how you get those besides just experience. So that's why I'm encouraging you to practice these and to look at the little trick that I used there. That was like a double trick. It was like if this were the Olympics, it'd be like a triple Lindy or whatever that they do in this. I don't know if it's the diving or don't they do the double is that the ice skating? Ice skating's coming up, I think. All right. So now let's kind of go through some other tricks besides the one that I just looked at, or the ones that we just looked at. Let's look at this idea of more cool tricks. Let's look at this idea of completing the square. By now, you can complete the square, hopefully. If you can't, well, then you're going to solidify this skill now. Completing the square is just it's just rearranging the furniture, and you do it so that you can get a perfect square trinomial, and then you can address issues, with this perfect square. Because a lot of those integrands, when you look at them on the sheet, especially all these inverse tangent ones and inverse secant, they all have something squared in it. So even if you had an x plus 1 squared, that would be helpful because you would be able to get it into this form. So the idea of completing the square is very useful, and it comes up a lot. So let's look at an example. Say we want to solve this problem, the antiderivative from 1 to 2 of 8 dx over x squared minus 2x plus 2. Now, don't just type this bad boy into your calculator. That wouldn't be fun. Okay? I mean, that would kind of take away all the fun on it. And, you could look at it for a second, that denominator, and you could think, does it factor? But there's nothing that's going to multiply to get 2 and then add to get negative 2. That's just not going to work anyway. So let's see if we can complete the square to create
your conference is scheduled to end in 2 minutes.
Trinomial. So let's just consider the denominator. All right, and we have this x squared minus 2x plus 2. Okay, so the steps to completing the square, the first thing you do is you group the variables together, okay? So we have this x squared minus 2x, and we want to think of them kind of separately from that plus 2. We'll worry about that plus 2 in a minute. So if we wanted to create a perfect square trinomial, which means that we could factor it as x plus whatever squared, what you do is you take half the middle term, you square it, and then you add it. But you also have to subtract it because you're really doing nothing. So you take half of 2, which is 1, and you square it, and that's just going to be 1. Okay? But since you added 1 here, you have to subtract 1 there. So we did half of negative 2, and then we squared it, which made 1, and then we also did a negative 1 because we really want to do nothing. Okay? That's just kind of a little note to ourselves. All right, and so then this factors. it always factors as the half value with whatever the sign is here. So this factors as x minus 1 quantity squared. It's a perfect square. And then this will just be plus 1. Okay? Now what that's going to allow us to do is when we take this and pop it back in here, we can write this then
Your
as
conference is now over.
antiderivative
Goodbye.
From 1 to 2 of 8 dx over x minus 1 squared plus 1. All right, and then this is what? What does it feel like? Brandon? Scott already knows, so I didn't let him tell me. Yeah.
So arctang.
Good for you.
Arctangent.
That's right. It doesn't feel very much like it, but it actually is the arctangent. This is the u, and this is the a, right? They're kind of switched, but with the plus, it's no big deal. And this h, just a constant, comes in front. So if you let u equal x minus 1, du is just dx, right? So we can put this 8 in front. We can change our limits so that we go from 0 to 1. We have a du, and if you want to be, you can put 1 squared minus u squared, plus u squared if that felt better. But anyway, it's u squared plus 1. So that's our a and our u. And so this is 8 times the arctangent, which you can write arctan. And it's always u over a, which in this case is just going to be x minus 1. And we're going to evaluate that from 0 to 1. And so this is going to be 8 times the arctan. Now just to mess y'all up, I'm going to put the negative one there to show you that you can use either notation. The inverse tangent of this will be 0 minus the inverse tangent of negative 1. All right. The inverse tangent of 0 is actually 0 because tangent is sine over cosine, and so that's when is the sine ratio 0, which is at 0. The inverse tangent of negative 1 is, anyone? No. Yeah, I see you. Stop that with your calculator and use your brain and tell me, because you took my trig class. When is the tangent 1? Look, I mean, how do you guys live? I mean, how do you exist without knowing this stuff? The tangent is 1 at 45 degrees when the sine and the cosine are equal. Duh. So it's pi over 4, but when is it negative 1? Well, then that's going to be at negative pi over 4. Okay. Now, if you had used your calculator, which I would have done when I was taking Cal 2, and that's fine, I would have remembered that pi over 4 was like 0.707. Do y'all remember that? And so your calculator would have given you negative 0.707, and you would have said, oh yeah, negative pi over 4. All right. Okay, and so then would we say negative pi over 4? And so then this is 2 pi. Okay, so wasn't that fun? Which one was that? Okay. Everybody good with that one? All right, so then I will move to, y'all want to do another completing the square? Do you feel like you need another one? Let's do one a little bit trickier. Sometimes if they have the coefficient in front, you have to factor it out. You can't, you have to handle that. So let me see. Let's do, 39. I'm working from the book, but on my notes, this is number 9. Okay, so this is the antiderivative dt over the square root of negative t squared plus 4t minus 3. Okay, and so,
down.
pardon? Move it down.
Down.
Is that good?
Yes.
More? Okay. So let's just consider this. Negative t squared plus 4t minus 3. All right, the first thing you want to do is group, but ditch that negative in front. So that's going to be t squared minus 4t. You with me? And then the minus 3 is just tagging along. All right, then you're going to have half of 4, which is 2, and then you square it and you get 4. Okay? So because we did half of 4, and then we square it, which is 4. But we really subtracted 4 right here. So, you all right? Can't see it.
Why is it not half of negative 4?
Well, it can be half of negative 4, and then square it, and it's 4.
Oh, okay.
It's always, you're always going to add right here. But that negative does help you in the factoring. It's going to be a minus when you're factoring it. Okay, now, I really didn't add 4, though. I added negative 1 times 4. So I really subtracted 4 right here. So out here, I have to add 4. Is that okay? Everybody okay with that? Because I really did negative times the 4. So little nuances that kind of mess people up. All right, and so then this is going to be factored as t minus 2 quantity squared plus 1. Okay? And so I guess to make it feel really good, you could write this as 1 minus t minus 2 squared. All right? So this is going to go in there. Okay? So all we did was rearrange a little bit. So now we will have the antiderivative of dt over the square root of 1 minus t minus 2 squared. All right, and then now you look at your sheet and you see if that looks like anybody. Mm-hmm. It looks very much like this number 16 on the sheet, the arc sign. So I will use the arc sign one, where this is my A is 1, but my U is t minus 2. But du is just going to be dt, so I'm good to go. I don't have any numbers that I put in front or anything. So this is going to be, what did I say, arc sign, which you can write arc sign or you can do sine to the negative 1. T minus 2 plus c. I don't know if the computer likes arc sign or if it likes sine to the negative 1. I don't have you guys, I haven't done any of these. Or whether it knows the difference. Does it know both? Okay, good. All right. Now, let's try another little trick. So that was the completing the square trick was a fun trick. And so now the next trick that we're going to look at is trigonometric identities. So this is trick 2. Okay, trick number 2 is your trig identities. And I did give you a trig formula sheet, at the beginning, or I provided it for you. I don't know if you printed it out or not. So if you need one, you might want to look at that. Let's look at the antiderivative of secant x plus the cotangent of x squared dx. When you're looking at this one, when you look at this one, the first thing you probably should do is kind of think about, do you know the antiderivative of any of these, or, what is it that you do know? If you look at your sheet, you should know or you should probably remember that the antiderivative of secant squared is tangent, because the derivative of tangent is secant squared, right? So if you were to FOIL this out, you would at least have that part of it. Let's see, what else do we know? We know cotangent squared. We don't have a cotangent squared one, but we do probably remember an identity that deals with cotangent squared, maybe. Okay, so I'm going to FOIL this out. and I'm going to get secant squared x plus 2 secant x cotangent x plus cotangent squared x dx. And I'm going to remember that secant is 1 over cosine, and cotangent is cosine over sine, right? So I can write this as secant squared x plus 2 times 1 over cosine x times cosine x over sine x. So this is just going to be 2 cosecant x plus, all right, cotangent squared x. You know, if you're on a desert island and you have to try and work these problems, and maybe you only have what you remember, one thing I always remember is that sine squared theta plus cosine squared theta is equal to 1. And then if I want to get a cotangent, I can divide everything by sine squared. And then I get that 1 plus cotangent squared theta is equal to cosecant squared theta, right? And so that means that cotangent squared theta is equal to 1 minus cosecant squared theta, right? Can you see that? Or you could have looked on your sheet and you would have seen that. Well, the good news about that is that you actually know there is an antiderivative for cosecant squared theta. So you can replace cotangent squared theta with 1 minus cosecant squared x dx. All right, so we should be pretty good to go here. We have antiderivative secant squared x plus 2. 1 over the sine is cosecant x plus 1 minus cosecant squared x dx. And we do have an antiderivative for cosecant on your formula sheet. It's an ln1. So each of these can be anti-differentiated now. The antiderivative of secant squared x is tangent x. Plus, if you look at your sheet, the antiderivative of cosecant x is, we'll have the 2, and there's a negative in the antiderivative. So it's negative 2 ln absolute value cosecant x plus cotangent x. The antiderivative of 1 is just x. And then the antiderivative of the cosecant, negative cosecant squared is, the antiderivative of cosecant squared is negative cotangent, so it's going to be positive cotangent x plus c, which I'm sure was exactly what you thought the antiderivative was. That's a messy one, huh? Okay, so that wasn't too bad. We just used some trig identities there to help us. Let's try another one of these with the trig identities. The antiderivative of the cosecant of x times the sine of 3x dx. Okay, what you want to do on this one, when you see that sine 3x, you actually want to use the sum formula for sine. So you want to break up 3x to be like 2x plus x. So this is the antiderivative of cosecant x. And actually, I'm going to kind of I'm not going to write the symbol each time, so I'm just going to be playing with this. So I'm going to do cosecant x, and then I'm going to do times the sine of 2x plus x. So instead of sine 3x, I'm going to think sine 2x plus x. All right, and then I'm going to remember the sum formula for the cosine is, anybody? If you look on your sheet that I provided for you, the sum formula for the sine of A plus B is sine A cosine B plus cosine A sine B. So it'll be sine 2x cosine x plus cosine 2x sine x for our problem. So we're going to have cosecant x, and then we're going to have sine 2x cosine x plus cosine 2x sine x. I don't know if you can even read that, hopefully. Okay, then remember we're just playing. We're just trying to clean this up a little bit. So what I'm going to do is I'm going to go ahead and distribute my cosecant through, and maybe some things will happen. Cosecant is what? What is cosecant? Right, and I need to do a little bit, let me do a little bit more work, because I know that cosecant is 1 over sine, which is good here because it's going to cancel, but it's not good here. So can I do anything with sine 2x? Do you guys remember the double angle formula for sine? Again, how is it that you're having a happy life? I'm not really sure. I can tell that you are all just miserable that you don't have this stuff memorized. Get a bad trig. Brandon had a good trig teacher. Look, I've even got it circled there. Sine 2a equals 2 sine a cosine a. This is the double angle formula for sine. That's worth knowing. I mean, it's worth sticking in there. It's kind of like that arctangent integral. I mean, this stuff. It turns up. You never know when you're going to need that on a cold day in the winter or something. All right, so sine 2x is going to be 2 sine x cosine x. Then we've got a cosine x here plus, we'll just do that, cosine 2x, and then we've got the sine x. Now, the whole reason we did that was because cosecant is 1 over sine, so it's going to cancel with this. Right? And so when you distribute through, your sine cancels. So you'll get 2 cosine squared x plus, again, your sine and your cosecant undo each other, so you just get cosine 2x right here. All right, now, this is almost something that we can integrate. What do you remember? Do you guys remember how to integrate cosine squared x? Yes, Mrs. Brooks, we use Wayne Duncan's favorite formula, and you are correct. If you look at your trig sheet for not once, not twice, but the third time, you will see, almost circled, that cosine squared a is equal to 1 plus cosine 2a over 2. And that you can integrate. You can't integrate this when it had the squared in it, but you can integrate just a plain old cosine 2a. It's just going to be sine 2a over 2. Okay, and so you are going to come back here, and you are going to go and say that this is, according to Wayne Duncan's favorite formula, 1 plus cosine 2x over 2 plus cosine 2x. And then, fortunately, these 2's cancel. And now, look at that. We've got 1 plus 2 cosine 2x. All right? So we cleaned that bad boy all up, and now we are ready to integrate it. So we will write this as the antiderivative, coming back here, of 1 plus 2 cosine 2x dx. The antiderivative of 1 is just 1. The 2 is going to tag along. The antiderivative of cosine 2x is sine 2x over 2 plus c. So these cancel, and you just get x sine 2x as the final answer there, which is really remarkable. You know, that cosecant x sine 3x simplified to the antiderivative of it is x plus the sine of 2x. Okay? So, yeah. Useless, yes. Fun, no. But, well, I don't know. I thought it was fun. But, I don't know. All right. I really like these. Improper fractions. This is trick. This is another. These are frictions. F-R-A-C-T. What to do when your fraction is improper. Now remember, an improper fraction is one where the top has a higher degree than the bottom, you know, or like 5/3 is an improper fraction. When you have 5/3 and you're in 7th grade, you immediately think 1 2/3, because apparently if you are a 7th grade math teacher, the improper fraction is the devil. Now, if you are a higher level math teacher, not that they're lower level, just if you're teaching a higher level math, you know that improper fractions are wonderful because 5/3 could be a slope, up 5 over 3. Makes a lot more sense than 1 2/3 as your slope, right? But anyway, back to, let's say we're in 7th grade. If we're in 7th grade and we were to see a problem like this one, the antiderivative of 2x cubed over x squared minus 1, and we want to do this from the square root of 2 to 3 dx, we would immediately recognize that this is an improper fraction, and we would want to write it as a mixed number or a mixed polynomial. And so, of course, if you have 5/3 and you want to make that as a mixed number, you put 5 in the house and you divide by the 3 and you see the 1 time and you have a remainder of 2, right? So that's what you're going to do here. You're going to do, yes, wait for it, long division. Oh, great. Yeah. And you're going to figure out what this is. Have y'all seen that movie? I mean, that show, How I Met Your Mother? Barney's always like, wait for it. I don't know, whatever. It's all, and they always says something really inappropriate. But okay, this is going to be what you do. Do you remember with long division? You put this in the house. So this will be, you do 2x cubed divided by x squared, which is just going to be 2x, and then you multiply 3 by here, and that's 2x cubed minus 2x, right? And then you, Brandon, what do?
Draw the line, change the sign.
Ah, there you go. You draw the line and change the sign. You had a good college algebra teacher. 2x cubed minus 2x cubed cancels, and then I have a 2x right here. Now, I'm done because this is a lower degree than that. That's like my remainder. So this is my remainder. So that means that this can be written as the antiderivative from the square root of 2 to 3. And instead of writing it like this, I can write it as 2x. Remember when you did 5/3? 3 goes into 5, 1. So there was your 1, and then your remainder. And then you said and 2/3, right? So this was your 1. So there's my 2x. That's my quotient. And the and is actually a plus. The remainder, 2x, over the divisor, x squared minus 1. Now, you can integrate both of these things, no problem. This one's just a little u sub, and this one's just a little baby one. Okay, so this is x squared over 2 with the 2 in front, the 2's cancel, so this is just going to be x squared. This one is a u sub, u equals x squared minus 1, so du equals 2x dx, which is exactly what you have there. So that's just a 1 over u, which is what? ln of x squared, absolute value of x squared minus 1. And you're going to evaluate that from the square root of 2 to 3. Did I skip too many steps there? Are y'all all right? You all right, Brandon? Yeah, okay. So now I'm going to pop in this stuff. So I've got 3 squared plus the ln of 3 squared minus 1 minus the square root of 2 squared plus the ln of the square root of 2 squared minus 1. So my answer is 9 plus the ln of 8 minus 4 minus the ln of 3. So this is 5 plus the ln of 8 minus the ln of 3. And probably, to be totally cool, you would need to write this as 5 plus what?
I'm sorry.
Where are you lost? Did I goof up? I could have messed up.
Is the square root of 2 squared just 2?
Yes. Square root of 2 squared is 2, not 4. I was going so good. 9 minus 2 is 7. So did I screw it up? I screwed it up in several spots. Crap. 2 here. 2 minus, so this is just 1. Are you happier now? All right. I was rolling really good, and then I messed it all up. All right, so how about our answer is 7 plus the ln of 8? It's no fun when the student corrects the teacher. Which number is that? I was so excited about my long division. Yeah, you got it right. 7 plus the ln of 8 is what they got to. Thank you. Sorry about that. You want to do another long division, or you feel good about long division? So he's good? All right, I got a good here. So now we'll do a different type of fraction. We'll do another trick. This trick is separating fractions. All right? So the separating fraction trick. When you have a problem like this one, what you should do is you actually have a monomial in the denominator. You have a single thing in the denominator, so you can look at that. You can separate, you have a binomial in the numerator, but you can write them individually. This is not an improper fraction because the bottom degree is lower than the top degree, right? So we're not going to use the long division technique. But what we can do is we can split this up, and we can write it as 1 over the square root of 1 minus x squared minus x over the square root of 1 minus x squared. Is that okay? Now, you can't separate your bottom up. You know what I mean? Like if it was, right, but you can separate your numerator and put it over the whole bottom. All right, then what is this guy? That's my arc sine. So this is going to be inverse sine of x. And what's this guy? Well, he's just a little u sub, right? So I'll go ahead and write it. Minus, if I do u equals 1 minus x squared, then du is equal to negative 2x dx. So I need a 1/2 in front, or I need a negative 1/2, which is going to make this positive 1/2 right there. And then it's going to be 1 over the square root of u du, which is u to the negative 1/2. So I add 1 to it, which is 1/2, and put it over it. So that's 2. So this is the inverse sine of x plus, the 2 is going to cancel with that. So it's just going to be u to the 1/2, which is the square root of 1 minus x squared plus c. Okay? Kind of fun. So that's the trick, a little trick there, separating fractions. Now, another trick that we looked at was, we already looked at this one, but I'll do another one, multiplying by a form of 1. So multiplying by a useful form of 1. Like, sometimes 7 over 7 is a useful form of 1, right? You actually learn that very early in your life when you learn how to add fractions. When you have 1/2 plus 1/4, if you multiply 1/2 by 2 over 2, a convenient form of 1, then you can add those fractions. So you've done this before. I'm going to look at the antiderivative of 1 over 1 plus the sine of x dx. So now, when I attack this problem from in my little brain's going, what are all the different ways that I can do this? The first thing my brain says is, oh yeah, this is not an arctangent because it doesn't have something squared. I've got to have that thing squared. And I'm totally out of luck because I don't have anything in the numerator that I could do. Like if I had a cosine x in the numerator, then I could do a u substitution, but I don't have that. So I'm really limited in what I can do. So that's when you have to start being creative. And one way to be creative is to multiply by a convenient form of 1. In this case, a convenient form of 1 would be the kind of the conjugate of 1, of the denominator. So if I multiply the top and bottom by 1 minus sine x, you'll see some fun things happen. So I will get 1 minus sine x in the numerator. In the denominator, I'm going to get 1 minus sine squared x. All right, and then I have my dx. Now, say you're having a really good day. What do you immediately recognize you have forced in the denominator? No, it's a trig identity. It's the world's most important trig identity. Yeah, you actually have cosine squared x in the denominator because sine squared x plus cosine squared x equals 1. So cosine squared x is equal to 1 minus sine squared x. So this is, I call it Big Daddy. So this is the antiderivative of 1 minus the sine of x over cosine squared x dx. All right, now might be a fun time to go ahead and split this bad boy up because you have a monomial in the denominator. You have just a single thing in the denominator. So what you can do is write this as the antiderivative of 1 over cosine squared x minus sine x over cosine squared x dx. Well, 1 over cosine is secant squared x, right? Which does seem to have an antiderivative. I think it's like the cotangent. Now this can be written as sine x over cosine x times 1 over cosine x. Sine x over cosine x times 1 over cosine x, right? Well, this is tangent x times 1 over cosine, which is secant x. And I think if you look on your sheet, these guys are familiar antiderivatives, right? The antiderivative of secant squared x is, I think I said cotangent earlier, but I meant tangent, is the tangent of x. And the sectan, the antiderivative of sectan is the secant. So this is going to be minus secant x plus c. So this is from sheet. The only way you get good at these is with practice. So, all right, that was fun. And then the final technique is eliminating square roots. Okay, so let's look at the last problem, number 15, that I'm going to do. The antiderivative from 0 to 2 pi of the square root of 1 minus cosine x over 2 dx. Okay, so if you want to eliminate the square root, you might just have to go back to your friend Wayne Duncan. And if you don't know Wayne Duncan, he's the math teacher that's been here at MCC since the beginning of time. And he's still teaching. And when I first started here, I haven't been here quite as long as him. And I wanted to put together that trig sheet that you have. And I said, to all the math instructors, I said, what are your favorite formulas? And he said, by and large, the most important formula in the world is this one. And he called it the Wayne Duncan's favorite formula. So that's where that came, or I called it Wayne Duncan's favorite formula. But if you go back to your trig sheet, let's find that. These two formulas just turn up over and over again. And so it's circled in blue right now, sine squared A equals 1 minus cosine 2A over 2. That is pretty much what we're looking at on number 15 if you can put your brain around how you could think about it. So we know that sine squared A is equal to 1 minus cosine 2A over 2, right? Which is exactly what we have here, except instead of 2A, we have an X, right? Do y'all agree with that? So if we let X equal 2A, it's weird A, then I can solve this for A, right? And I would get X over 2 is equal to A, right? So instead of sine squared A, if I want to make a replacement here, I'll say sine squared X over 2. Does that make sense? Because my A is X over 2. So this will be the antiderivative from 0 to 2 pi of the square root of sine squared X over 2 dx. And why is that great? Well, the square root of sine squared is just sine, right? So I can think of this as the antiderivative from 0 to 2 pi of the sine of X over 2. Now, we would need that to be in absolute value. When you take a square root, you have to think of that. You have to worry about that, you know. So this does in fact need to be in absolute value, and it kind of depends. If your X is ranging from 0 to 2 pi, you don't need to worry, because that means that X over 2 is ranging from 0 to pi, and between 0 and pi, the sign is positive. Okay? So we do normally need to have those absolute value symbols there, but we don't have to worry about them in this case, because the sign between 0 and pi, which is what would happen when you divide by 2, is positive. So we can just think of this as the integral from 0 to 2 pi of sine X over 2. And then if your u is X over 2, then your du is 1/2 dx. So you got that 2 in front. So this is going to be 2 with a negative, because the sign integrates negative, cosine X over 2, evaluated from 0 to 2 pi. And so then this is going to be negative 2 cosine pi minus cosine 0. And so you are going to get negative 2 times negative 1 minus 1, which is positive 4. Now, don't be a loser and work that problem with your calculator just because you could. Yeah. I mean, I try to come up with ones where your calculator won't give you the nice answer. But, of course, if you have an 89, you can get the nice answer and take away all of your learning fun. But I wouldn't do that, because, I mean, what's the point? All right, so when you're eliminating these square roots, a lot of times, especially when it's with trig, you're just going to do some sort of trig substitution, so you can get, like, so a Big Daddy or a double angle or a Wayne Duncan or something like that, so you can get in and get that working. All right, so I will encourage you, I will put up the solutions like the instructor solution manual. And if you wanted to go in and just work all of the problems that are in the book, I did a bunch today, I did 15. You can go in the text, he's got like 7 or 8 additional examples. The best way to get good at these is to practice them. And then when you take the test, you'll have fun instead of fear. Okay. All right, so I'll see you guys later.